Hey everyone, thank you so much for joining us today at the Data Streaming Summit. My name is Dipankar, and today we are going to talk a little bit about how to achieve high throughput streaming in Lakehouse architecture with non-blocking concurrency control in Apache Flink and Apache Hudi. All right, let's quickly share my screen. Right, perfect. All right, so before we get started, a little bit of introduction about me and my co-presenter. My name is Dipankar, and I currently work as a staff developer advocate at Onehouse.ai. I have been involved with the Lakehouse space for quite some time now, and contributing to open source projects such as Apache Iceberg, Apache Arrow in the past, and more recently Apache Hudi and Apache Xtable. And I'm joined by Sagar Sumit, who is a software engineer and an Apache Hudi PMC member. And Sagar has also contributed to numerous other projects in the big data space, such as Trino and Presto. With that, let's get started with our talk. All right. So let's take a step back to understand how Hudi started, right? Because the problems that we're seeing at Uber, and that's when the Hudi started actually, back when Uber was in a hyper growth mode. So they were moving from a data warehouse to a data lake environment, right? And the problem was whether you have cloud object storage or on-premise Hadoop file system, it is an immutable storage system, right? So you had to put kind of a database or a transaction layer on top of the data lake to work with it. And that's how basically Hudi originated. So the problem that Uber ran into specifically was with the trips database. Like everyone else at the time, they were doing bulk inserts, and this process took up to 120 terabytes every 8 hours to convert from the old format to Parquet, and then they would do a full recompute of all the downstream tables again, and so the end-to-end data freshness would be around 24 hours. So they noticed their ingest performance was really bad, with a ton of unnecessary reading, writing, and I/O and compute spend, without any guarantees that the job would finish successfully, right? And we are talking about massive tasks, right? Massive jobs that might just fail without any guarantees. Plus, there were no concurrency control mechanisms, no asset guarantees, rollbacks, nothing of that sort. So this was the basis of how basically Hudi started. So when Uber started to tackle these problems, they realized they weren't facing a completely new problem, right? Pretty much all of the database system dealt with these kind of challenges. It is just that they needed to figure out a way to implement these in a way that it fit their data lake environment, right? And essentially, what they decided was if they could build a system that could be capable of handling update, deletes, and upserts, so you could absorb the changes faster into a table form, right? And while they are able to do those things like faster updates, can they also query a snapshot consistently, right? So that way they have no dirty data and it see things are either committed atomically or not. Plus the ability to look back at specific point in time, right, and do things like time travel, which is very important as well. And in case there are some mistake, you can track back to when things were right and basically do a rewind, right? Also, it wasn't just the ingestion problem, right? There was also the need to incrementalize the downstream ETLs, right? For instance, can we consume only the changes instead of the full recomputation, right? Only those changes that has been made. And that led them to build incremental changes, which is very core to Hudi and also separates it from other open table formats out there. And again, while all these writes and reads are going on, there is also the need to manage and organize data optimally, right? Pretty much like a database where you have an internal process that manages the database. So they implemented a couple of services in Hudi called table management services, which work together and manage this table format. So all these principles guided the core primitives of Hudi, which is like, upserts, ability to absorb changes to records and process them faster, incremental reads, snapshot isolation, which basically allows you to read the latest committed state consistently without any kind of dirty data. So once Hudi had all these capabilities, the resulting architecture was basically like a database abstraction for cloud storage. And especially by decoupling storage and compute, so now we can have faster upserts, different type of indexing schemes were built in Hudi, which again is very unique to other table formats with indexes in Hudi. And you can incrementally build ingest tables, right? So incremental processing as a concept actually pioneered from this. For example, instead of ingesting, like we said, 120 terabytes of data every 8 hours for Uber, they could just now absorb a few gigabytes of data every 10 minutes. And this makes for really efficient ETL downstream. Uber actually builds most of their core warehousing tables in an incremental fashion, where they actually process only the incremental changes every few minutes and then run it. This is not as ubiquitous as it could be today, but we focus a lot on that aspect with Hudi. Okay, so moving on, we have come a long way from those humble beginnings, right? From those kind of transactional data lake, kind of a database layer on top of data lakes. And thanks to the diverse community contributions that today Hudi serves as an end-to-end Lakehouse platform overall. So coming to our point, like what's a lake house, right? And as you might have guessed from the name, it's a combination of the data lake and the warehouse of some sort. But of course, this is not just a mere combination of the two architectural pattern, but the whole idea is basically to take best of the both world. For instance, data warehouses, they have great data management and optimization capabilities, right? Things like compaction, clustering, metadata tables, and the ability to do things like time travel, schema evolution, upserts, deletes with async guarantees. Uh, and similarly, coming to data lakes, right? They provide the scalability aspect of it, right? Especially now with cloud object storage like S3, Azure, Google Cloud. Cost-wise, these object stores are very cheaper comparatively, right? Which is really great for a customer standpoint. So a lakehouse basically builds on that idea, and one of the core ingredient or component in the lakehouse is basically the table format and the storage engine layer. So Hudi provides an open table format, but also it's important to know that Hudi is not just a generic table format. It has integration of various table services, various platform services. There are ingestion tool, native Hudi writers. So that actually makes Hudi a end-to-end lakehouse platform versus just being a table format. So if we talk about the various components, I'm not going to go too deep on that. But assuming you have been reading a little bit more about lake houses, the components itself are you have the storage. If you start from the bottom, you have the lake storage, you have the file format, the table format. That is basically the transactional database layer, and then you see all the compute on top of it, right? Whether it's Flink, whether it's Spark, any other compute as well. And then you have other things like catalog, which is also part of the architecture that allows with like visibility and kind of a record keeping of sort. So that's what typically makes a lakehouse architecture. The one important thing to note over here is that this architecture is not any different from a traditional database management system, right? The only difference being that all this component that we talked about, they are bundled up into one single system, a monolithic system in a traditional database management system, right? Whereas in a lakehouse, all of these things are pretty much modular and open. So you really have the flexibility of choosing the best component for your workload, right? Whether it's batch ETL, whether it's streaming, you really can choose your compute, you really can choose your catalog and the set of tools that come with it. All right. So now let's delve into some of the specifics of Hudi by going over the Hudi's table format and how it kind of lays out the files in a distributed file system. So two logical concepts that are important here to understand are one is the file slice and the other is the file group. So a file slice basically contains a base columnar file, which is typically Parquet, and it produced at a certain commit or compaction time. And it also comprises of a log file that contains the update to the base file since the base file was produced, right? But one important thing to note over here is that the log file only comes into the picture for a specific type of table type called merge on read table, where the idea is to basically do your changes merge on at the time of reading and then kind of like making sure the writes are more faster and low latency wise. And when we have a group of such file slices, we call them as a file group, right? So when a write comes in, the records are written to these file slices, and each record is actually given a key that is mapped to a particular file group. And this assignment, it never changes, right? That's kind of the mapping. So it's kind of a primary key in a way to understand like, what record has what key mapped to a particular file group. So in terms of the advantage of having this particular file label layout, first from the point of writing to a Hudi table, if you have multiple table services running in the background alongside the ingestion, the services don't block each other, right? Because of like things like concurrency control. And second, from the point of view of querying the Hudi table, the file layout allows query engine to query a table at any point of time, right? And again, do things like time travel. So on the bottom half, you see two important things here. The one is the timeline, and the other is the metadata table. I'm not going to go too deep on this, as Sagar is going to cover that part. But the timeline is basically what keeps a record of all that has happened in the commit action in Hudi. And the metadata table is basically a way to reduce extensive file listing and stuff for better query planning. So that's another important aspect. All right. So now that we have an understanding of Hudi's Lakehouse platform, I would like to introduce a streaming ETL approach using the integration of Apache Flink and Apache Hudi. So this combination it uses the strengths of both the technologies to create an efficient real-time data processing solution. So our process begins with data ingestion. In real-time data architecture, Flink usually consumes upstream messaging data sources like Pulsar or Kafka, performing continuous processing on incoming data. Uh, so it produces a change log kind of stream, which is then synced into a Hudi table. And what sets this approach apart is the support for incremental processing that we talked about, right? So the Hudi table serves as both as a sink and a streaming source, and it generates new change log stream for further processing. So thanks to the incremental semantics that are defined by the Hudi table format, and this allows dual functionalities of being both a sink and a source, and that allows operations like SQL joins and aggregations, allowing us to create bronze, silver, and gold table for various analytical needs. And this type of architecture is typically called as like the medallion architecture, but let's not go with the nomenclature there. Um, so Flink as a stateful computation framework, it excels at consuming this incremental changelog and basically accumulating those intermediate results. However, one thing to note is that the state backend that Flink that stores the intermediate results in Flink isn't optimized for large-scale analytics, and that's where Hudi comes in as a materialization layer, right? So Hudi supports this native row-level upserts and deletes, and it excels in both streaming ingestion and consumption. And by combining Flink and Hudi, we have created an incremental streaming ETL pipeline that addresses these limitations of traditional batch processing, which ultimately reduces latency and opens up new possibility for real-time data analytics. So now, we know that Hudi works as a materialization layer for changelog produced by Flink, right? But how does that work exactly? So the solution relies on Flink's dynamic table concept. In Flink, a changelog stream is typically referred to as a dynamic table. So it dynamically represents the same results as a batch snapshot table, reflecting all the changes for each row in a real time. So in Flink's processing pipeline, it consumes one dynamic table and it performs continuous queries and computations and generates another dynamic table. This allows for multiple operations in a single pipeline before syncing those change log to the downstream. So using this Flink's dynamic table, Hudi introduced the changelog mod in release 1.0.9 pretty early on, specifically to work for this particular scenario, right? And this feature has been widely adopted in production environment. So changelog mode in Hudi is a straightforward implementation where we kind of preserve all the changes exactly as they come in, right? So in Flink, we have the row kind column in the dynamic table, and this row kind column, it represents different type of operations, right? Whether it's insert for new records, update before and update after for updated records, delete for removing records. And on the Hudi side, we introduce a new metadata column called Hudi operation. This column's job is to basically record the row kind from the Flink dynamic table. So when writing to the Hudi merge on read table with Flink, Hudi's log file will buffer these changes until the next compaction run. So therefore, any readers that can consume these changes as a streaming changelog source during that window between the current write and the next compaction, right? Now, Hudi's order preserving characteristics also helps achieve this particular goal. But one limitation of this approach is about the upstream source for Flink. It has to support the state changelog derivations. For example, a stream of changes produced by DBZM, of course. And if the upstream stream data cannot be interpreted as a changelog, as in new versions of the record just come in as is, Hoodie's changelog mode won't be able to work for this changelog readers downstream. All right, so that's basically what the Hudi Flink integration looks like and how we have implemented that. Now I will hand over to Sagar, who is going to touch upon the new NBCC method for Hudi Flink integration. Sagar, over to you.
Thank you, Dipankar, for the overview of Hudi. Hello, everyone. I'm going to be talking about non-blocking concurrency control. Um, So streaming ingestion is all about processing large volume of changes with very low latency, right? And to bring the Hudi tables throughput to another level, I'm going to walk you through this exciting feature that we released in Hudi 1.0 version. But first, let me motivate the problem. Historically, we have viewed data lakes primarily through the lens of batch jobs. And the go-to method of handling multi-writer scenarios has been optimistic concurrency control, or OCC. But with OCC, jobs typically take a table level lock to check if they have impacted overlapping files. And if there is a conflict, what do they do? Well, the entire operation is aborted, an operation that could have costed a massive amount of resources. So imagine two writer processes, a streaming ingest writer producing new data every few minutes, and a deletion writer enforcing GDPR compliance, which takes like an hour to issue deletes. So these jobs are likely to overlap files with random deletes, right? Causing the deletion job to starve and fail to commit each time. Um, so OCC check fails, you restart the commit, you see again there is an overlap, the OCC check fails. This is not going to scale for high throughput ingestion that streaming systems require. OCC was designed for immutable or append-only data, but it's inadequate for incremental processing or handling fast updates and deletes. The key problem is the assumption that OCC makes that the contention is not going to happen. It's optimistic in its assumption. But in reality, conflicts do occur frequently, especially when you have high throughput streaming ingestion coupled with long running deletion jobs or any long running job for that matter. In database speak, this is like mixing long running transactions with optimism. And the longer these transactions run, the higher the probability they will overlap and conflict. So Hudi took a different approach right from day one, and it always treated regular ingestion writers and table services differently. Um, the foundation of all these, by the way, by table services, I meant the background cleaning or compaction jobs, and we'll see that. So, but the foundation of all these concurrency control mechanism is an atomic and consistent timeline per table. We will go into the detail of the timeline in a few minutes, but let's summarize what Hudi had until non-blocking concurrency control. So the default was multi-version concurrency control. It isolated long-running services like cleaning and compaction from the regular ingest writers, and it satisfies most needs. But Hudi did OCC to protect against two writers or multiple writers writing to the same file group at the cost of retries. But we'll see shortly, this is what NBCC, with NBCC, the writers never fail. Hudi serializes them after the fact. So let the writers continue. After the fact, use a commit completion order. Let's look at a happy scenario first. Writer 1 updates the red file group. Writer 2 touches the green file group, as you can see on your left side of the slide. OCC check passes because these are two distinct file groups. MVCC keeps the background compactor on the right side, reading a stable snapshot. And this is a very common scenario. OCC isn't that bad. It's just brittle when writes overlap. Let's see what happens on collision. Same two writers, but now both update a common file group. So writer 1 commits first. Writer 2 OCC's check flush time, sees a newer instant, and it aborts. So now there is a rollback and retry, which leads to duplicate shuffle, wasted network, higher end-to-end latency overall. And that's exactly the bottleneck that non-blocking concurrency control removes. So in next section, we'll dive into how NBCC lets both commits succeed and stay ordered. And in order to understand that, it's very important to understand the fundamental building blocks of NBCC. And it's not that complicated. Those fundamental blocks are mainly two. First, the timeline. The second, the main invariance that the system has to honor, irrespective of what. So let's look at the timeline first. Everything in Hudi is driven by the timeline, which is an append-only event log that records every mutation of the table. The moment, so Hudi has two notions of time, even within the timeline. So there is a requested time, and another notion of time is the completion time. The requested time is the moment an intent is registered. Think of it as, I plan to commit now. Completion time is when the action is durably finished. So every action on the Hudi table moves from this requested to in-flight to completed state. And we snapshot at the completion time, not at the requested time. So separating the two gives us the freedom to overlap work, yet still read a totally ordered history. As you can see in this diagram, writers can fire off commits in parallel because only requested time must be unique at scheduling. The heavy lifting happens later on, and readers replay actions strictly by completion order, giving deterministic output even when requests arrived out of order. But here's the catch. How do we generate those timestamps so that every writer across JVMs, across data center agrees on the order? And that's our next topic. So to keep the time monotonically increasing, we need a single source of time truth. Otherwise, two writers could just pick the same instant and we would corrupt the log, right? So Hudi implements a true time API, which is inspired from Google Spanner. Google solved this with very high precision GPS and atomic clocks. Great if you have Google's CAPEX, but also the requirements on our side is not something like guaranteeing external consistency at very high throughput. So Hudi chooses a cheaper path. It uses a lightweight mutex. So what that entails is all writers grab a very short-lived mutex on the timeline. They read the last issued timestamp, and if the current time in milliseconds is less than or equal to the last issued, then they sleep the estimated worst case clock skew. Now, this worst case clock skew is configurable. By default, it's a few milliseconds. Eventually, they will release the lock and write the new instant. So the critical section is only the timestamp allocation. The key thing to note here is if the timestamps are allocated in a safe manner, then writers need not stay blocking for all the heavy I/O. And generating this timestamp in the safe manner, in practice, adds only microseconds of latency and yet guarantees global monotonicity. So we now have trustworthy instants. Next question is, how do we store millions of them? See, you could be making commits every minute and you need to store 10 years worth of data. That means millions of commit meta files in Hudi metadata. And you can't be doing ls on the Hudi metadata folder every time, otherwise it will just explode. So now enter the LSM timeline design, okay? Conceptually, LSM tree, log structured merge tree, batches hot inserts into the memory and then flushes sorted runs to disk, which is perfect for a write-heavy log. And that's what our timeline is. It's a write-heavy, immutable log. So the way the timeline is structured in Hudi, so level 0 of this LSM timeline design is essentially the last few hours of instance, which is queried constantly by the writers and streaming readers. Well, it could be, it also depends on the commit frequency. If you're committing less frequently, then it's not just last few hours, could be last couple of days. But essentially, this is like the active timeline queried constantly by the readers and writers. While level 1 and 2 are compressed timeline segments, Compaction merges older commit meta files into these coarse grained files. So we compact all these level 0 timeline sometime in future into these level 1. Um, uh, and these are our columnar Parquet files. So what are the benefits of this? First, the active timeline stays up to a constant order of entries, and lookups. So lookups like what's the completion time for a given requested time becomes a single binary search down the levels, which is like sub-milliseconds on cloud object stores. Deletes and archival happen as whole segments, so you don't have to pay tiny file tags. Timeline can scale indefinitely and still answer the ordering question that NBCC relies on. So let's see the invariance. We talked about the timeline, right? To recap the key benefits of the timeline, first is the key design components of the timeline. The first is the timestamp generation. Um, should happen in safe manner, globally monotonically increasing. Second is the LSM timeline design. Now let's talk about the invariance, right? Recall that I talked about two building blocks, the timeline and the invariance. Um, so mainly there are two invariants, the key invariant and the file slice invariant. Let's see what they are. Hudi requires a primary key, and the key invariant states that a given record key is deterministically hashed to one file group ID. And that mapping never changes. So two writers updating the same key will always land in the same bucket. No duplicate rows downstream. So that's the key invariant. Okay. What's the file slice invariant? Dipankar talked about file groups, log files, base files, and how file groups comprise different file slices. So the file slice invariant says that inside a file group, each log file belongs to the slice whose base requested time is less than or equal to its completion time and is maximal among such bases. So a lot of words, let me break it down. So let's say you have two writers writing log files, and then you compacted to produce a v1.parquet and log files, a bunch of log files. Again, you compacted to produce v2.parquet. Let's say these compactions. Let's take some timestamps, right? So T1 writer one, it starts writing to the log file, completes the commit at let's say T3. Then another log file write T2 starts at T2, completes at T5. Imagine if to the same file group, there was another writer which completed at T2, writing to three different log files. So what this means for the compactor is, and let's assume that the compactor started at T4. So we have a couple of log files due to writer one, which started at T1 and ended at T3. One log file started at T2 and ended at T5. Then a bunch of log files due to writer two started at T1 and T2. No, note that the writer one is concurrent with the compactor as well, because compactor started at T4. So in the view of compactor, uh, that log file T2, T5 is in a different file slice. So all these log files, the ones written by writer 2, the one and the top two log files written by writer 1 are part of the same file slice that will be compacted. While T2, T5 is in another file slice. Why? Because T5, the completion time is greater than the maximal base requested time. So maximal base requested time in this case is due to the compactor, which was requested at T4. So T2, T5 log1 will go to another file slice. So a lot of mechanics here. I just want to say that this leverages the versioning nature of file slice, which is very, very important. If there was no versioning within the file slices, it would be very hard to resolve the conflicts. So when writers write to the same file group in a Hudi table, we name the log file suffix in a non-conflicting way using distinct writer tokens. So what if the commits have conflicts? Basically, we resolve them using compaction, which will merge the log files with the base Parquet files in the file groups. During this merging process, records from the candidate log files and the candidate log files is chosen on the basis of that file slice invariant. Those candidate log files will be extracted and merged using a user-defined event time field for determining the record order. So by design, compaction jobs need to be scheduled to determine what log files to be included for the compaction execution. And we don't want to block the compaction scheduling or writing either. So we need to make a call about which log files can be scheduled. So that criteria, the file slice invariant criteria, is log file having commit completion time less than the compaction start time, because the compaction start time forms the maximal base requested time. I hope this clarifies to an extent. There is an RFC with a very good example. I'm really not sure if the slides do the justice, but I've tried my best to illustrate the point. But you can always go to the RFC and go through the example. Um, so the invariants ensure the correctness. Now, the main takeaway is why this is so powerful. Your writers can continue writing to the log files. Compaction can run mid-flight without pausing the writers. It just ignores the logs whose completion time is still in the future, right? So, and readers can reconstruct the table by scanning slices in the completion order. So all deterministic, no lockstep needed. With these two invariants plus our monotonic timeline, non-blocking concurrency control delivers zero write conflicts and consistent reads, all while Flink keeps every writer at full speed. That's the crux in like 18, 20 minutes for you. I would like to thank the community at this point. All of this would not have been possible without a very lively community over the years. Hudi community has grown to significantly 19 PMCs and 36 committers from diverse backgrounds, different companies. Our GitHub engagement is well above 6,000 users. And in just last couple of years, we have answered around 5,000 questions on Slack, serving 4,000 plus members, which is still increasing. And if you haven't already given us a follow on LinkedIn or Twitter, please star us, follow us there. If you love and use Hudi, you can scan the QR code to join the Slack community. And thank you for listening patiently to this presentation. We are here for any questions. Thank you again.
All right.
Hi, Sagar and Dipankar. Thanks for coming to the live Q&A.
Absolutely, yeah.
Uh,
Yeah, I was able to take some questions offline, but yeah, I'm happy to answer anything else, yeah, with Sagar.
yeah, just for the sake of the recording, I want to just bring up the one about can you highlight some differences between Hudi and Iceberg? And you did link to the blog post. And for those
Right.
watching the recording, there's a blog post at hudi.apache.org, and I think it was from March 5th. The 21 unique reasons why Apache Hudi should be your next data lakehouse. But you mentioned that one of the main things is for write-heavy workloads, low latency. And
Mhm.
Hudi's on object storage, correct?
Correct. Yeah.
And
Yeah.
object
Hudi.
storage isn't typically low latency. So I want to get your opinion on what you mean by low
Yeah.
latency there, or what optimizations Hudi does that make
Yeah.
it better than other data lake
Absolutely.
architectures.
For sure, yeah. So yeah, I mean, typically like Hudi is so one of the main differentiation between Hudi and the other Lakehouse like formats. We talk about open table formats, but Hudi is kind of an open Lakehouse platform as well because it just is not about the metadata format, which is basically what we call it as an open table format, but it also has its own like kind of native writer, like ingestion service, like it has its own table management services, which is pretty much open. Like you can do compaction, clustering, sorting, and those kind of things, which really are important for your performance benefits. So those are there by default. So you are not outsourcing it to a computer or something else. So that basically kind of gives the leverage of being a Lakehouse platform. So that's kind of one of the main highlight. But specifically in terms of like when I meant low latency, it's pretty much what I'm referring to is kind of like, you're writing at a much higher, like faster frequency. Um, so that means kind of like our streaming-based workloads. That's where like we're talking about Flink and Hudi. So those kind of thing can really benefit from Hudi's unique design. For example, like Hudi has like the concept of indexes, and I talked about like how we kind of like mark that with the the exact file group mapping, right? So because you're able to keep a track of those level things, and you can easily like do things like upserts and in a more faster fashion, because you know exactly where in the file system that record exists in the particular Parquet file. So yeah, that's basically what I was referring to. But Sagar, if you want to add something else, yeah.
Oh, yeah, absolutely. So we have to put this low latency in context as well. I was at a meetup and I remember this fintech company in India. I think it's called Navi, and they do commits every 30 seconds.
Right.
Uh, and try doing that with any other format out there, which does not support rich indexing like Hudi does, which are utilized heavily on the write path. You want to update without having an efficient way to figure out where the update records are located. You will not hit those latency requirements. So yeah, the high throughput as well as lower latency. That's where I think Hudi excels a lot. And the concurrency control. In this talk, we mainly focused on concurrency control. There is a lot of rich indexing within Hudi, inbuilt in Hudi, that goes into, and I think the Flink writer uses the bucket index. That's a perfect example of that.
Exactly. Yeah.
All this content is out there in Hudi blogs. I think that will certainly help in understanding. And feel free to reach out to us on Hudi Slack.
Yeah.
We can dive into the mechanics of how each of these work.
I think the other thing, Dipankar, you mentioned was there's built-in compaction, because I know in a lot of the other sessions it comes up
Yeah.
who's doing table maintenance. So in this case,
Right.
is most of the table maintenance built in?
Yes, so that's what I primarily meant around. So basically, what Hudi also brings is kind of like the storage engine part. If you talk about traditional database system, it has this like kind of the storage engine, right? And like for example, like MySQL has like InnoDB and MyISM and those kind of thing. So basically, you're able to bring in that kind of capabilities by default within the Hudi's APIs. So all of the services are basically service, right? You can just call them, invoke them within any kind of writer. So compaction, clustering, Z ordering, any kind of like multidimensional sorting, those are really inbuilt with Hudi, and that kind of takes off the responsibility of like scheduling it with other kind of like things introducing into your data pipeline, which can be super kind of like complex at times. The other thing that I wanted to mention is around basically since Hudi does it natively, you also can, like Sagar also discussed in this in the presentation, but we are aligned with the timeline, right? We are basically trying to understand like what is happening in the timeline, and writers can take action based on that. So you can also have abilities like asynchronous like compaction or asynchronous clustering for that matter. So versus you are scheduling those job in a maintenance period with other formats, we are talking about doing that coordination within the writer with Hudi natively, so you don't have to like do that with your compute engine, and they don't have to talk with different writers and manage that with other concurrency control techniques. Yeah.
Cool. Anything else to add, Sagar, before we wrap it up?
No, I think I'm good. I would just like to thank everyone who attended this talk, and thanks to Stream Native for giving us this opportunity to talk about all the cool things that the Hudi community is building. I would
Absolutely.
like to ask everyone here to just give it a try, give it a spin, and give us feedback. Yeah.
Yeah.
Yeah, thanks for the talk. We've heard a lot about Iceberg, obviously, so it's nice to have a more in depth about Hudi.
Absolutely. Yeah.
So thanks so much for coming. I think that the closing remarks have started most likely. They might even be wrapping up already, but I'm gonna head on over there.
All right.
Thanks everybody for coming to this talk.
Bye.
Right.
Yeah.
Thank you.